Hello students, this video, I'm going to stop here. Hello students. Hello students, this video, it comes on top of that selection sort video, which was a YouTube video by what I consider to be a very clear and popular instructor. This selection sort video is closer to the assignment that you have. In fact, it would, I'm guessing, cover the assignment for a couple of modules. The first one dealing with sorting and the other dealing with searching. As you know, when data gets very large and we have, let's say, 100,000, let's say, movie items, the time taken to look or search through movies gets longer as our database gets longer. Because if information is kept unsorted, then it's not clear whether the information we're looking for is at the beginning of the pile or at the end of the pile. So every single time we are looking for things, we are scanning the entire list. That's what a linear search does. You start at the beginning and then you keep searching for your data item, and you are often not sure that it's even there. So in which case you have to look at the entire pile, or it may be it could just be the first item. You could have gotten lucky, or it could be in the middle. So that's why we say the average time to search for through a linear pile is about half the number of items. Now, as the data gets very large, this average is not good enough. What we'd like to have some kind of clarity about how long is it going to take to search my item. The first thing that comes to our mind is, wouldn't it be common sense for us to keep our information sorted? So just like a phone directory, imagine if we had an unsorted phone directory and we were searching for our friends' names and everything from A to Z was jumbled up, then it would make it so much harder for us to search for our friends. Whereas if we kept everything sorted in alphabetical order, then for sure we would be able to reach our friends much quicker. So the first step in making our searching easier is to keep data sorted. And there's a variety of techniques to sort the data. There is a bubble sort, which I think you might have done in 301. And there's quick sort, which you would do in 400, which is a recursive sort. And one of the good, fast, efficient sorting mechanism that we will cover in this class is called selection sort. The selection sort algorithm is in your textbook. It's also been explained in detail in the previous video, but I'm just going to go over it just a little bit to say, well, here's how roughly the selection sort works. I'm just going to get myself a pen. And say, let's say we have some items here, and I have 6 and 4 and 9 and 11 and 2. Then the way the selection sort works is it works by selecting a position, which is in this case this position, and making sure that as we keep proceeding down our pile, we are able to get, if you're doing the sorting on ascending order basis, then the smallest element is placed here, right? So why selection sort? Selection sort because you start, let's say you start from the first element, and then you compare this element to all the elements in your array, for example, and then finding the element that is less than, that is the least element when you compare to this, right? And then switching the position of 6 and 2, right? Now, note that the way this works is slightly different, because what's happening here is you're comparing 6 to 4, and then you find that 4 is smaller than 6, but you do not switch yet. Then you compare your 4 to 9. So this one is greater than, so you disregard it. Then you compare 4 to 11, greater than, disregarded. And then you compare 4 to 2, and then you know that 2 is less than 4. So what we are going to do is we're not going to swap 4 and 2, but we're going to swap 6 and 2, because the least number that we have found is 2, and our task is to put the least one in position. So we select the 2 and we move the 2 here, and now our array is going to look, it's going to look like this. The 6 has gotten moved here. The first pass does not leave the array completely sorted. It has only put the smallest position in the place. Now we're going to move to the next position, and the same process begins all over again, except that now we don't need to worry about 2 because that's already sorted. So then we start to compare 4 with 9. 4 is still smaller. 4 with 11, it's still smaller. 4 with 6, it's still smaller. So in this case, we need to leave everything as it is, right? And then now let's go to the next, our next task of, so now our array is still looking like 2, 4, 9, 11, and 6. And now we come here, and 9 is less than 11, so it is fine. And then we compare 9 to 6, and we find 6 is smaller, right? So 6 is smaller than 9, so we say all right, but we don't have any further comparisons to make. We've reached the end. Therefore, what we are going to say is that the minimum index is, if this is 0, 1, 2, 3, and 4, then the minimum index, the index at which we found the minimum is 4, and that is what is going to get called as the minimum index. And we are going to swap this one with the number at the minimum index, which is this. And then our array is now going to look like 6, 11, and 9. Now you see we've skipped over the 11, and we still have an unsorted array. So now we cannot stop. We have to keep moving up to here, to the next element. And then we say, okay, let's compare 11 with 9. And then we find that 9 is less than the minimum. The number at which the minimum is found is, the index at which the minimum is found is 4. And 9 is the value that is present there. We switch them, and now finally we get 2, 4, 4, 6, 9, and 11, and our array is sorted. So as you can see, the selection sort in this particular situation caused us to do 1, 2, and then 3 passes till we found that our array was completely sorted. So to recap, the selection sort, it concerns finding the place where you have the least value and switching the current position with the least value. So so that's what the selection sort does. And what I'm going to do now is I'm going to erase all of that and go over this example right here. I'm going to go over this example and show you a movie data file which has got the name of the movie, the director, the year, and the time taken. And this program, what it does is it creates an array of movies, and then it reads all of the movies from the file into an array, into the movie array. It sorts the array and then prints the array. And after it prints the array, it also does a binary search. Now, I'm not going to go over in this particular video, or maybe I should. So, and then it searches. So here, I would like to point to you the construction of the movie data record. a movie, if so, your chapter 7 contains a lot of details on what a record is, and it is important at this stage that uh, you read through that and do the simple examples that are given in that chapter, or in the section of that chapter. As you can see, a struct is a compound data type. So far we've been dealing with integers and booleans and character and string, but sometimes we want to have a hospital record or a movie data record. And so this is your structured type. And now what we do is we are now constructing an array. We can construct an array of structured types. So now we've got an array of movies, and each movie contains fields which has information about the title of the movie, the running time, the year, and the director. Now, when we do our selection sort, the criterion that we are using for our sort to compare movies is the running time. That's an integer, and that's the simplest comparison. So therefore, what we are saying when we do the selection sort here is we say, let the minimum index start with the very first element in the array, scan the rest of the array to find the position where the least element occurs, and then switch that least element with the current position, right? So this is a nested for loop, and I have actually written a selection sort procedure for this movie data type. So what I'm doing here is, for example, if I have these movies, and as you can see, the first movie had running time 60. The first movie had 60, and then the second movie had 276, and the third movie has 110, and the fourth movie has 213, and then the last movie had 200. Now remember, this is not just running time here, but this is a complete record. I'm only writing down the running time because it would just take up a whole bunch of space and time, but know that this is the movie Lightning Speed, this is the movie Beetle Bailey, this is the movie Curious Case, this is the movie Why Monday, and this is the movie The Godfather for G. So all of this information is right here inside the array, but the only item that we're interested in is the field running time, because that's what we would like to use for sorting and comparing. So the first time we find I, let's say this is our I is equal to 0, right? I is equal to 1 here, 2, 3, and 4. And so the size of this array is 5. I start with I equal to 0, as you can see here, and go all the way. I start here, and I would go, whoops, this is zoomed. All right. So start with I equal to 0. And as you can see, it goes to size minus 1. So I less than size minus 1. We want to start here, and then we want to stop our comparison here because we would like to take this item and compare it with the last item as the last comparison. So we start here at I equal to 0. And as you can see, I set my min index is equal to I. So at this point, my min index is equal to 0. And I also create a temporary movie data type. And what I do here is I also have another variable which is called my min value. And min value is equal to movie data I dot running time, which means initially I set my minimum value to be what's contained in at the 0th position. So here it's going to be 60. And these are variables are going to be very important for me to perform the selection sort. So I'll start with I equal to 0. I've saved these values, and now I'm jumping into my nested loop and starting with j is equal to I plus 1. So my j is actually going to start here. J is equal to I plus 1. So here's my j and here's my I. Now, so I take this element and start to compare it by moving j across to the end of the array. So what I'm comparing now is if data j dot running time is less than minimum value. Now remember, I've saved the minimum value of the ith position in min value. So what I'm saying here is if the element at the jth position is less than this one, the one that is stored in min value, then what I have to do is I have to say I found something smaller, and I'm going to say min value. So that now if I find something smaller, which I have not, then I've got to do a swap. So the first time I'm going to go through all of them and find I don't need to do a swap because I've got the smallest one here. Then I move to I is equal to 1. So my I moves to this position, and and I still have at that point. Now I say my min index is equal to I. So in the second round, my min index now becomes equal to 1, and my min value becomes equal to 276. So this is 276. And then my j is going to start from I plus 1. So my j is going to start at 2. So I compare 276 with 110, and I find that I found a min value. So what I'm going to say is my new min value is actually equal to 1110. And I'm going to say my min index, current min index, is not equal to j, is not equal to 1, but it's going to be equal to 2. Because here's where I found, right? And then what I'm going to do is, now I'm going, my j keeps increasing, and I'm going to check, is the value at j less than the minimum value? I.e., is it less than the least one that we've found so far? In this case, we find it's not. And when we move even further, we find that it's not less than 110. So this, in fact, is the next least that we have found. At the end of this whole journey of going from j plus 1 to the end, we have found a new minimum. And now what we'd like to do is move this into this position. So here's what's happening here. I say if I need to swap, i.e. if I found a minimum value, then what I'm going to do is I'm going to move this. So this happens, this is what happens. I have saved this in the temp, the data in this in temp. So I say, now I'm going to move, instead of 110, I'm actually going to move this here and move this here. So 276 goes there, 1110 comes here, and now the second element in my array is actually now sorted. So this is how the selection sort happens, by selecting a minimum value in the rest of the array and switching the current value with that one. So, so I'm going to erase all my drawings right here. And so this is an explanation of how this algorithm works. The other thing that I wanted to point out is so as you can see at the end of it, initially I had an unsorted movie array, and now all of them have been sorted in ascending order according to the running time. Now, once the data is sorted, it becomes easy for us to search. One very, very powerful search mechanism is called the binary search. And the way the binary search mechanism works is that, because just as in its name, binary search, it divides a sorted array into consecutively every single time into two parts to narrow down the area of search and therefore try to trap the target element that we're looking for. Now, the premise for the binary search is that our data needs to be sorted. So let's assume that we start with sorted data right here, right? And let me So this is where in the piece of code you've done the selection sort, and now you ask the user for, would you like to search for a movie, and the user is able to supply a search time and say, I'm just looking for a 60-minute movie. Can you find the 60-minute movie for it? So, and then you do a binary search on your movie array and you return the index at which you found it. And then you print that particular. If you cannot find it, then you have to say, I don't find it. So, of course, we're going to make our passengers' life easy by displaying all the movies, a sorted list of movies available, and then they can select it by running time, and then they can get the movie that they want. So let's just quickly go over binary search. Now in binary search, let's say I have my movies all sorted. I have 60, 110, and then I have 200, and I have 213, and then I have 276. So now again, as usual, my array index is going to be like this. And let's say that I would like to search for the movie with a running time 276, right? So the first thing that I'm going to do in my binary search is I'm going to say, let me divide this into two parts. The way to divide it into two parts, if you look at the binary search algorithm right here, I'm just going to show it to you and then redraw the stuff. So here is, in fact, maybe I should do this here. I've got 60, I've got 110, 200, 213, and 276, right? And so now so the first thing we do here is we need a first, we need a last, and we need a middle, because we'd like to divide this area into two parts first. So these are some of the variables I'm using for first, last, and middle, and saying my first initially is I is equal to 0, 0, 1, 2, 3, 4. I've got 5 elements, and so my first is going to be 0. My last is going to be 4. How do I calculate middle? I calculate middle by saying my middle is the first plus last divided by 2. 4 plus 0 divided by 2 brings my middle right here. So this is my first, and this is my middle, and this is my last. Now, so what I do is, while I have not found it, or my search area hasn't become so small that it has become non-existent, I can keep dividing and conquering. So the first time I have my entire array, I divide this into two parts, and I say, okay, I'm looking for the number 276. So let me get the middle of this array, and then I compare my 276. So that's what's happening here. If movies.middle.running time is equal to time, the time that we're searching for, then say found is equal to true, you found it. And you return the index at which you found it. Otherwise, what we need to do is we need to say, if the time is less than, if the number that we're looking for is less than the middle number, then we know that it's going to be in this area. If it's greater than, we know it's going to be in this area. So now I compare 200 with 276, and I know it's greater than, so there's no point looking in this area at all. And I say the region that I need to look at is this one. So I have, in a binary way, I have divided my array, thrown away the first half because it's not likely to be there, and then I move my first to middle plus 1. So my new first has come here. And now I need to recalculate a new middle, which is going to be 3 plus 4 divided by 2. So 7 divided by 2 is going to be equal to, in integer division, is going to be 3. And so my middle and my first are both converging, which is fine. So as you can see, this is a repeated process where every time we find a new first or a new last, and also definitely a new middle, compare every search item to the element in the middle of the array, the new middle of the array, and then decide whether we found it or we need to go left or we need to go right. And so here in this case, we need to go right. So now I'm going to do a comparison with the middle and find that 276 is to the right of, and now so I need to find a new first and a middle. So then I say, all right, I've got to go move here, and my first is middle plus 1. So my first and last now have converged. And it turns out that 4 plus 4 divided by 2 is 4. So first, last, and middle, everything has gotten converged here. And as we can see then, the middle element does turn out to be 276, and we found it. And so we return the index 4. So you see, if we return the index equal to 4 here. And if by some chance we have not found it, then we return -1. And that's likely to happen, for example, if you were looking for the number 300. We know 300 is not here, right? But we moved our first to here, and we moved our middle to here. And if this number was not equal to 300, what we'd say is 300 is greater than first. So we would try to move our first to, our first would be equal then to 5, and our last would be equal to 4. So we have exceeded, our first becomes greater than. So this condition is no longer valid. Our first now becomes greater than last. And so we've crossed all the areas and we've searched everywhere, and now we cannot find it. And therefore, we are going to stop and say that did not find it and return -1. So that's how the selection sort and selection and binary search are going to work for an array of struct.